Hello everybody, and welcome to the review of Newton's first law, your solution video. So we'll go ahead and start with number 1 here. Force diagram for a block sitting at rest. So we're going to draw our block. Sitting at rest, we know that the forces are balanced, and since it's just sitting at rest, no applied forces to it, we have force due to gravity and then the normal force. So now for number 2 again, we're drawing the force diagram at constant velocity. So what we know about constant velocity is that constant velocity is going to, and we'll call this on a frictionless surface, so there it is. We know that the forces must be balanced. So the normal force is going to equal the force due to gravity, and as it has been stated before, at rest is a zero velocity, and a zero velocity is constant. So now we'll move on to number 3. What is the relationship between the two force diagrams above and y? Well, they're the same, so there's your relationship. They are the same. And then y, because zero velocity is constant velocity, because 0, and I'll just call v for velocity, is constant linear velocity. And when it's frictionless, we don't have to worry about any applied forces, frictional forces, that whole cat and that whole thing. So now, what do unbalanced forces do to an object's velocity? Unbalanced forces change velocities. They change velocities. They change an object's motion. Because otherwise, if there's no unbalanced force, if the forces are balanced, an object will keep on doing what it's doing. Number 5. Number 5, we are drawing a force diagram and calculating the forces of a 9 kilogram block sliding across a table from left to right with friction acting at 32 newtons to make it slow down. So we'll go ahead, we'll draw our block, draw our table, and this guy is sliding. But to go along with that sliding, there's friction, so it's sliding left to right, and friction is acting at 32 newtons. So this block, we'll say, started here, and it's sliding this way, going that way. And actually, that is a poor diagram there. The block would be moving to the right. So that means that the applied force, when it got moving, would have been there, and then the applied force leaves, and now there is friction acting on this object. So the friction, as it's moving left to right across here, the friction force will be going backwards. It will be going to the left, be going against the motion, and that is at 32 newtons. Now this block weighs 9 kilograms, so that means that my force due to gravity, which is equal to the mass times the gravitational field strength, will be 9 kilograms times 10 newtons per kilogram. So that means that F of G will equal 90 newtons. And if that is 90 newtons, that means that my normal force will be 90 newtons. And number 6, draw the force diagram and calculate the forces for a 7 kilogram block sliding across the table left to right at a constant velocity with friction acting at 84 newtons. So here, we've got a block I didn't give myself a lot of room to draw the forces here, but that's okay. Here we have force due to gravity. We're going down that way. Force due to gravity. We have a normal force. And now the block is going from left to right at a constant velocity, and friction is acting at 84 newtons. So here, friction is counteracting this, but it's at a constant velocity. So the constant velocity means that we need some other force here. And here we will have the applied force. Now for these values, the force due to gravity, that will be 7 kilograms times the 10 newtons per kilogram for the gravitational field strength. So again, m times g, and we will get 70 newtons, which is also the normal force. And now friction, so here we have friction is 84 newtons, and then to keep that moving at a constant velocity, that will also be the applied force. We'll call that FA. So now we'll move up here to number 7. Drawing the force diagram and calculating the forces of a 75 kilogram table being pushed from right to left across this page at a constant velocity with 92 newtons of applied force. So here we have our table, kind of a heavy table. It's being pushed right to left. So being pushed right to left, that means that the applied force will be heading to the left because that is the direction of travel. So here we have the applied force, which means that to keep moving at a constant velocity, we need friction to be on the other side and to equal that. And again, I'm trying to draw my arrows, my vectors of proper magnitude and direction. So the directions are accurate. The magnitude, the arrow should be the same length. So we've got force due to gravity on this table, and then we've got the normal force coming up from the ground. So now to solve for these, force due to gravity is the mass, 75 kilograms, times the gravitational field strength of 10 newtons per kilogram, for a total force due to gravity of 750 newtons, which then must equal the normal force. Now the applied force it gives is 92 newtons. So we have 92 newtons, and to be moving at a constant velocity, that must be the same as the friction force. Now we move on to number 8. Draw the force diagram, calculate the forces of a half-kilogram hockey puck being slowed down by a stick by applying 15 newtons of force to the right of the puck. So we can start out with a drawing here. We've got ourselves a hockey puck right there, and it is being slowed down by an applied force from a hockey stick. Again, I'm a great artist, so there is the hockey stick. So now we get to our forces here. We'll always have that force due to gravity, and then since it's going to be on the ground, we have the normal force, equal and opposite to counter that. And now we have the hockey stick is applying a force of 15 newtons to the right of the puck. So if it's applying the force to the right of the puck, that means that the applied force will be heading to the left. It's applying the force to the right to slow it down. So we have an applied force of 15 newtons. So that one is already given to us, 15 newtons. Now we have the mass of the hockey puck is 0.5 kilograms. So force due to gravity is mass times the gravitational field strength to give us a force due to gravity of 5 newtons, which will then equal the normal force as well. And now on to number 9. Draw the force diagram. Calculate the forces of a tug of war where the team on the left applies 650 newtons and the team on the right applies 545 newtons. So here we'll start off, got our rope. We'll draw the old tug of war rope in there. And then we've got a few people. So we've got some people in there. They're pulling on a rope. Pulling on the rope here. This guy's not even pulling on the rope. We'll get him over there. There we go. So we got him pulling on the rope. And now the team on the left is applying 650 newtons. So here we've got a force applied of 650 newtons. And the team on the right is applying 545 newtons. So who wins the tug of war and why? Well, the tug of war will be won by the left side here. It's won by the left side because they are applying more force. They're applying 650 newtons while the team on the right is applying 545 newtons. They will win the tug of war, so the rope will be pulled more to the left. There's your Newton's first law review. Enjoy, enjoy, enjoy Newton's laws.